So historically, optical interfaces started out as one wavelength, which worked really well up to 10G, and then at 40G we transitioned to four wavelengths, which has been the paradigm that has dominated data centers. Several years ago, we recognized that there will be a need for more wavelengths, that increasing baud rate and modulation order will not be sufficient, and we wanted to lay the foundation for higher wavelength count optical interfaces. We didn't want to get restrictive in terms of a specific application, so what we focused on was standardizing the wavelength grid, leveraging both what the ITU-T and IEEE had done. Typically in optical interfaces, what takes the most effort is the laser development. So we focused on that, and we defined laser grid and key specifications around laser sources, but we left the applications till later and to individual implementers. How do you think we've done since we started the MSA, Matt?
Well, it's been an interesting journey. If you think back all the way to 2020, when we first announced the standard, there was a lot of focus on, as Chris mentioned, what are the applications for this? What are some of the long poles? How does the standard map into some of the previous standards which had been developed? And as time has gone on, now what you're starting to see is this notion of the standard starting to take hold. We're starting to observe suppliers, actually multiple suppliers, start to offer core technology, especially some of the laser technology, which Chris talked about, now available into the marketplace. Chris, maybe you can tell us a little bit more about what you're hearing about from an application standpoint.
The promising direction is really computer interconnect. Ethernet's been traditionally a networking application within the data center. But computer buses are naturally highly parallel and low latency. And if you want to go to optical interconnect, as some of applications like disaggregation just beyond the board or even adjacent cards require optics, higher wavelength count or parallel in general is a much more natural technology. Let me give you an example of PCIe, which is now looking at both copper and optical cable interfaces. That's a bus up to 16 lanes. So if you were to translate that to optics, that would be, minimum of 16 wavelengths or even 32 wavelengths if we wanted to reduce the modulation order. So I think, computing, which includes AI, ML, HPC, is probably going to be where we'll see the first applications of the MSA. How about some specific examples?
One of the interesting things about the MSA, especially as we move forward, is this notion of people within the supply chain aggregators, as well as test and measurement folks start to adopt the standard and offer products. A good example of some folks on the supply chain side are Macom Technologies, Sievers Photonics, and Lumentum, all who are world experts and offer world-class technology around some of the high-risk items, and some of the specific areas which Chris mentioned can be long poles for any technology development. On the aggregator side, we're starting to see people take those technologies and put them into end products. A good example of this is some of the work that Poet Technologies is doing. On the test and measurement side, Quantify recently announced a technology and a product which will be one of the first products to test for weather photonic integrated circuits, which are one of the end applications which the CW-WDM MSA is designed to support. Whether those photonic circuits can take the technology which the MSA defines and use it for their end applications. The CW-WDM MSA is proud to have several promoter and observer members participating and exhibiting at this year's Optical Fiber Conference in San Diego. Please visit their booths to explore the new technology that they're developing and what they're offering.